So this lesson's on trigonometry, written and presented by me, John LeGuy. Here's all the legal stuff. Right, trigonometry is actually all about things moving in circles. Later on I'll also show you that it also involves triangles. Using a familiar type of graph paper, trigonometry relates to a line that's moving around the circle. Here's a little Excel spreadsheet which I hope will explain this a little bit better. So this spreadsheet's actually available to you to download in the download links page. Now what I've got here is a line which is exactly 1 long, so it has a radius of 1 because it's going to be travelling in a circle. As I make the line travel around the circle, it makes a right angle triangle with the point here at the end here is a certain amount up and a certain amount along. The x value, which is the amount across, is a set amount for every angle. And the y value, which is the amount up, is a set value for every angle. Similarly, the ratios of the y, for instance, the amount up divided by the x, these are set and unique values for every angle. We also have a ratio which is the ratio between the amount across, the x value, and the radius. Now, the radius in my case is 1, and that ratio, the amount across, divided by the radius, is unique for each angle. And the amount up, the y value, divided by the radius, is unique for each angle. We have a name for each one of these ratios, and the name we have for the ratios are the ratio of the x divided by the radius. We call that the cosine. The ratio of the y divided by the radius, we call that the sine. And the ratio of the y divided by the x, we call that the tangent. And these are unique values for each angle. Now, where I'm saying that there is a unique set of values, strictly speaking, this only actually applies in the first 90 degrees, the first segment, this part of the circle. To show you what I mean, if I was to take an angle like 30 degrees, and it has a y value, a height of 0.5, and an x value, a distance across of 0.87. If I increase that to 150 degrees, you'll see it has the same height, because over here it's the same height as over here. And if I take that all the way round to 330 degrees, you'll see that that's the same distance across. However, since all right angle triangles will have angles, must have angles which are less than 90 degrees, and we will be primarily dealing with right angle triangles, we don't need to worry about that. So to all intents and purposes, there's a unique set of ratios for each angle. So this whole trigonometry thing sounds very complicated, but it's not really. All it is there are unique ratios for each angle. Just think of it as a sausage machine. And angles go in and ratios come out. That's all that there is to it. Where we can use this is with triangles. As the line moved around in the circle, it formed right angle triangles, and each angle had a unique set of ratios. Let's have a look at this triangle and the naming of names. We typically call the angle by some type of Greek letter. In this case, I've used theta. We do this to make ourselves look clever. The side opposite the angle, we call it the opposite. The side alongside the angle, we call it the adjacent, which just means alongside. The long side is called the hypotenuse. Now, that's a funny kind of word. And if you think about it, where it came from is the sort of things that they used to build out of triangles, like this pyramid. Here we've got it, you can see it's a right angled triangle that's sitting on the long side. The long side, the length of the base, which is now the underside, that's called the hypotenuse, because in Greek that means the length of the underside. Anyway, back to our triangles. Each angle has a unique set of ratios, and each angle has a unique set of ratio. The sine machine, you put an angle in, and out comes the ratio of the opposite divided by the hypotenuse. The cosine machine, you put an angle in, and out comes a ratio of the adjacent over the hypotenuse. And the tangent machine, you put an angle in, and out comes a ratio of the opposite over the adjacent. So, to summarize, every angle has unique ratios of sides. These ratios have names, we call them sine, cosine, and tangent, where the sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. Remembering these values, there's various ways. I often use oranges have segments, apples have cores, and oaks are trees. Some people use SOHCAHTOA. The way this works is, first equation, opposite over the hypotenuse equals sine. That's the SO part, or oranges have segments. The second equation, adjacent over the hypotenuse equals cosine. That's the co part of SOHCAHTOA, or apples have cores. And the third equation, opposite over the adjacent equals the tangent. That's the TOA part, or oaks are trees. We often abbreviate all of these words, opposite, adjacent, hypotenuse, sine, cosine, and tangent, to just the first three letters. Makes it easier to say them. So where do we use trigonometry? Supposing we want to find the height of a tree. Doink. I know that I'm standing 25 meters away from that tree, and the angle from the ground to the top of the tree is 40 degrees. Now what I've got is a right angled triangle. And what I want to find is the height, which is the opposite. It's opposite from the angle. The function which is going to be the most useful to me on this one is going to be opposite over the adjacent equals the tangent. Because I have the angle, I have the adjacent, and the one that's missing is the opposite. Rearranging that to give opposite by itself, and then I put the numbers in. Opposite equals 25 meters times tangent of 40. Now I look up the tangent of 40 in the table or using my calculator, and it gives me tangent of 40 equals 0.839. I just multiply the 25 meters by 0.839, and it comes up with 21 meters. So the height of the tree is 21 meters. Similarly, here, another example. I have a radar which has picked up a bomber, and it's picked up that the bomber's distance is 30,000 meters away from me at an angle of 2 degrees. What I want to find is the height that the bomber's at, which is the opposite, and the ground distance, which is the adjacent. To find the opposite the height, the equation that's going to be useful to me is opposite over hypotenuse equals the sine. Because I want to find opposite, I have the hypotenuse and I have the angle. So, rearranging that, opposite equals hypotenuse times sine of the angle, theta. Putting in the values, hypotenuse is 30,000 meters and the angle is 2 degrees. Looking up, the sine of 2 degrees gives me 0.0349. Multiply that by the hypotenuse and it gives me that the opposite is 1,047 meters. So the bomber is at an altitude of 1,047 meters. Now to find the ground distance, that's the adjacent. The equation that's going to be useful for this one is that adjacent divided by hypotenuse equals the cosine of the angle. Rearranging to give adjacent equals hypotenuse times cosine. Put the numbers in. Look up the cosine of 2, which is 0.9994. Multiply that by the hypotenuse, which is 30,000. And I get that the ground distance is 29,000 meters, 29,982 meters, about 30 kilometers. If you remember back to Cartesian and polar coordinates, we also used these functions to move backwards and forwards with those. Here's a point on my graph. It is a certain amount across, which is the x. It is a certain amount up, which is the y. It's also a certain distance from the center, which is the radius, at a certain angle, which I call theta. So, once again, this is a right-angled triangle. Just shrink that a little bit. And in Cartesian coordinates, we would put that point down as an x and y coordinate. In polar coordinates, we would put that down as a radius from the center, from the origin, and an angle from the horizontal, which is theta. Going from Cartesian to polar, we can use Pythagoras' theorem to give us the r value, the radius. The theta we'll find using an inverse tan function, which we'll do in the next lesson. Going from polar to Cartesian, we use the trigonometric functions cosine and sine. So, in summary, if you have a right-angled triangle, one of the angles, either that one or this one, the length of one of the sides, either the opposite or the adjacent or the hypotenuse, you can use the trigonometric functions to find the length of all the other sides.